All right, guys. So this is refraction 8 and 9 based on, or all about bending and changing speed of light. So a lot going on with refraction, especially Snell's law, where we're actually using the thing. So we have light with a wavelength. Oh, look, there's that side of the image. Light with a wavelength of 500 nanometers travels from air into an unknown material so that its incident angle is 45 degrees, but it's refracted to 30. So if we were to draw that over here, I recommend drawing it. We're going from, it said air, right? Yeah, it's going from air at 45. So we're going to draw that. That's 45 degrees. That would continue on straight. So we draw that nice dashed line as though it's continuing straight, but it's refracted to an angle of 30 degrees. So that means it gets smaller. So we're going to go down here, and that is going to be 30 degrees. So this is our N1, N2 material, right? This is air, so that's 1.0. We don't know the refracted material yet. All right, air, right, unknown there. So that's our kind of setup there. Determine the index of refraction. So since you have both angles and we know one of the index of refractions, we are going to use Snell's law to come up with that. So Snell's law is just N1, the index of refraction for the first material, times the sine of the angle in that material. And that's the incident angle usually, but it doesn't really matter as long as you match them. That's going to equal N2 times the sine of the angle in the second material, or the N2 material. Again, it doesn't matter as long as you match them. So we can just look over and plug in the stuff. So N1, we're going to call air. So that's going to be 1.00, times the sine of 45 degrees. That's going to equal our unknown N2 times the sine of 30 degrees. That's our equation there. And when you solve that out, again, we don't have to use the inverse sign here. We get N2 equals 1.41. And usually we'll ask what material that is. It doesn't necessarily ask you what material it is in this one, so I'm not going to go look it up yet, unless we have to. But yeah. So, and again, another thing to note: no units on N. Index of refraction is just a ratio, so you don't need units for that thing. So now that we know N, though, we can find the speed in that material. Remember, N equals C over V. But that equation, so that's the one from your sheet, that equation becomes V equals C over N when you rearrange it. And then we get 3 times 10 to the 8th divided by 1.41. And that's going to come out to be about 2.13 times 10 to the 8th meters per second. So that is our speed of light in the new material. Definitely slowed down. What's the wavelength and the frequency of light in the unknown material? Well, we'll use that velocity equals wavelength times frequency. The first thing we need to do is find the frequency of the first material there. So we're going to jump all the way back up here, and we see it's a wavelength of 500 in air. So in air, so we'll have 3 times 10 to the 8th. This is actually pretty difficult. It's kind of a multi-step here. Equals the wavelength, 500 times 10 to the negative 9th, all right, times the frequency. So that's going to tell us the frequency of that light originally, probably think it's green light, is going to be 6 times 10 to the 14th, I believe, 14th hertz. So that is our frequency in the material. It's also the frequency in air. And we can use that and the new speed to find the wavelength in the new material. So in the new material, with same equation, velocity equals wavelength times frequency, but now the velocity has slowed down. The velocity is 2.13 times 10 to the 8th. That's going to equal our new wavelength times the frequency that doesn't change. Frequency doesn't change. So 6 times 10 to the 14th there. And we do that out, we get a wavelength. Wavelength equals, I believe it's 3.55 times 10 to the -7th, right? I don't know. It's about that, and that's going to be 300. Yeah, I think that's right. And that's going to be 355 nanometers if you wanted to, but you could leave it just like that as long as you include meters on that. All right. So now we're going to kind of sketch what light is doing. So we're going from air into diamond. Now, we want to read the question. Make sure you read the question so that you label all the things. Don't just, I mean, you could go in and just draw all the things, but you don't want to forget something because it's going to be keyed for each of the items. And if you only do 3 of the items and we're asking for 4 things, it looks like we're asking for 4 things here: incident ray, refracted ray, incident angle, and refracted angle. And then you want to circle away or towards. You want to make sure you do all the things. So, yeah, so we're going air. We can label the incident ray right there. I, it's coming in. So we're going from air into diamond, and then it's going to, it's going to jump into glass after that. You want to make sure you draw the normal. I don't know, does it ask you to label the normal? No, it just says draw the normal line. So there's another item you want to do with that. So there's the normal. Now, again, you don't have to do this, but I like to draw what it would do if it kept going straight, so that it's very easy to draw towards or away. If I'm going from air to diamond, we are definitely going to bend here. All right, we're going to keep going, and then we're going to hit that other material right there. So then we can label our angle. So we did our normal line, label it in. Oh, I need to label it in. And then we are going to refracted ray. So that is R. But then R turns around and ends up being I on the next one. Oops, let's see, there we go, and then we want to label our angles. So we can label the incident angle. Now that's a weird way to label it. I'm just going to label it theta I. And then we'll label this one theta little r for refracted. And so those are our angles. And then did it bend towards or away towards the normal? Well, this one right here got smaller. It bent towards the normal there. So we will say towards the normal there. And the second surface here, we'll label the normal again. In, I'll do what if it went straight, but this case it's going from 2.2 down to 1.7. So we're going to bend away because we're getting to a smaller index of refraction. And there's my angle of refraction. And I have an angle of incidence. This is my refracted ray, 1, 2, 3, 4, and we are now bending away from the normal because we're going from diamond 2.42 index of refraction into glass 1.7. We're getting smaller, and so we're going to bend away to make a bigger angle of refraction than angle of incidence. And that is page number, I don't know what page number this is. What are we on, page 4? I don't know. It's questions 8 and 9. All right.